Okay, so then radiation exchange between black surfaces. Now we're talking about how you actually go about modeling these systems. Here's just two examples. Let's see if we can maybe zoom in a little bit. So for radiation exchange, what we're trying to do is identify all the pathways for radiation to flow between surfaces. Here for this example, we have a three-surface problem. If you have three surfaces, you can usually break that out and actually write out the resistance network and solve it. If you have more than that, it's a little bit tricky, so you have to kind of be careful. In the case that you have more, you need to go through the systematic approach like we did with the homework, where you write out the set of equations and duplicate loops and solve them simultaneously. For two or three surfaces, it's usually quite a bit easier. All right. So what we're looking at in this example is sort of what we talked through in lecture. You have these black surfaces. So the node is EB1. It's right at the, it's sort of interacting with the other surfaces. We have adiabatic surface here. This is EB2. And then we have another surface here, EB3. So what we're doing is just going through accounting for the resistances, right? Geometric resistance. And we're just sort of mapping out the heat flows and things like that. So what we did in our example in lecture was we said, okay, well this is adiabatic over here, so I know Q dot 1,2 is equal to Q dot 1,3, so that's one pathway. I know Q dot 1, or sorry, I did the same thing in the last. Q dot 1,2 is equal to Q dot 2,3, right, 2,3. And that's a different value from Q dot 1,3. So you have to somehow solve for these different values, but you can do that with the resistance network that we've got down here. All right, so if we're just concerned with what's going from, say, 1 to 3, then we would write out this equivalent resistance and solve the problem like this. Okay, but I think the point that maybe a point I want to add on to what I had originally presented was, for these types of problems, I think what you want to do is, if it's a three-surface problem, you can write it out. The resistance network, you can write that out. What you want to do is just be intentional about what you're trying to get out of it, and realize the equations that we've written up here, these are kind of like, we're trying to get out some heat flow from 1 to 3, so this is why we've set it up this way. It's not that you'd always do this equivalent resistance, right? This is for the specific problem we're trying to solve. So just be kind of thoughtful about how you set up the problem. Think about what you're trying to do in the end, and write the equations that correspond to that thing you're trying to do, as opposed to just regurgitating what you see here on the slide. In the case then when we have no adiabatic surfaces, so this is, you have maybe heat flow in each of the nodes. There we have to do energy balances on each node, and then solve that system of equations, okay? So again, I recommend going back and looking at this, but are there any questions on the black body radiation exchange stuff? Okay. Okay, so then radiation characteristics of real surfaces. Now when we're talking about real surfaces, keep in mind that a real surface emits less radiation than a black body does. And that real surface may emit less in certain wavelength bands, right? It can be spectrally dependent. So we would write the emissivity here for a given wavelength as the ratio of the actual power emitted at that wavelength to the black body power. And then that's saying that the emissivity can vary as a function of wavelength. If we say that there's no dependence and there's no directional dependence, then we get back this total emissivity here, which is just the ratio of the two, which is the integral over all wavelengths over the black body, which is the one we're familiar with here. Okay, so there's these different sort of levels of detail. There's epsilon, lambda, theta, phi, which is a directionally dependent, spectrally dependent. There's epsilon lambda, which is just spectrally dependent, but not directionally dependent. And then there's the total one, which is dependent on nothing. And then the last thing I'll add here, these down here are gray surfaces. Okay, and then radiation characteristics of real surfaces. There's two things to think about here. One is Kirchhoff's law, which states that for a given wavelength and for a given direction, theta and phi, absorptivity of a surface is always equal to emissivity of a surface. Okay? Again, that's a tough one to wrap your head around, but it's a simple law, but a little bit subtle. So this is true for this situation always, for real surfaces, for ideal surfaces. If you have a diffuse surface in which there is no angular dependence, then you can say absorptivity equals emissivity for a given wavelength. If you have a diffuse gray surface, these will go away. It looks like this, right? Absorptivity is equal to emissivity. Okay? So it's only under the conditions of a diffuse gray surface where absorptivity is emissivity for all, it's just in general. Okay, then the other thing here is surface energy balance. This is saying if I've got some irradiation coming into a surface, the irradiation can be absorbed, it can be transmitted, it can be reflected. The three possibilities have to equal 1 on a fractional basis. If it's a diffuse surface, you can simplify it. If it's a diffuse gray surface, you can further simplify it. Okay. All right. And then I think this is second to last one here. So diffuse gray surface radiation exchange. So what we did then was we took this idea with emissivity not equal to 1. And in order to account for the fact that light is reflecting from surfaces, not just being emitted, it's also going to be reflected and then go to other surfaces, we introduced this idea of radiosity. Okay, radiosity is a flux. It is watts per meter squared, so it's like energy per area. But it's the combination of what's reflected, rho times g, where g is a radiation, and what's emitted, epsilon times EB. Okay, that's our definition of radiosity. Once we have that, we can characterize problems in terms of these surface resistances. So a surface resistance is this additional impedance to heat flow related to emissivity, a non-black emissivity. And then if it is black, if the surface is black and emissivity is 1, then the radiosity is the same thing as the black body emissive power. All right, and we just represent the heat flow, the sort of virtual heat flow from the emissive node to the radiosity node as in terms of this resistance Rs, right? And keep in mind, like this isn't actually like a physical flow of heat from one place to another. We're just saying that there's an impedance to being emitted, and so we measure that in terms of a resistance, and we can write it as a network. Okay? And then if we want to write this out as a full radiation network, now we have this radiation exchange problem. This is again for 3 surfaces. The radiation exchange between surfaces' black body emissive power and its radiosity is related by that resistance. It's the same formula as we had in the last slide. If you want to relate radiation heat transfer between 2 surfaces, that's Q dot I to J, or Q dot IJ, that would be the equation Ji minus Jj over R Rg Ij, where the resistance is related to the view factors, right? So the core thing I think to keep in mind here is this was the subproblem for black surfaces. When you add stuff to the black surface, when you add emissivity of not equal to 1, now you have to add on these resistances, these virtual resistances, right? Again, this is not heat flowing from one place to another. It's an additional impedance associated with the surface. Yeah.
For the surface resistance, is that at the emitting surface?
It's,
you would kind of draw on a resistance network?
yes, it's at the emitting surface. That's right. Yeah, and it's not like, it's got the same units as the geometric resistance, but it would be like, conceptually what you think of it is like the heat moves to the surface, and so it's like there, and then to be emitted into this radiation problem, there's an additional hurdle it has to get over, and that's the emissivity of the surface. So you add this additional resistance in there to account for that, what looks like an effective temperature drop, right, to get to that, that radiosity temperature.
In lecture on Monday, you said that at an adiabatic surface, it's kind of like a black body.
Right.
Do you still want us to draw out the surface resistance then? Or that-
Yeah, so the question was, if it's an adiabatic surface, do we have to draw both the radiosity node and the emissive blackbody node? In that case, no, you don't have to. So like if let's say, all right, if this is a adiabatic surface here, you wouldn't have to include this because we know it's adiabatic. You could just say, okay, J2 here. You could also just say J2 is equal to EB2, and I'd be happy with that. But if it's not, if that resistance is not important to the problem, you don't have to include it.